Hi to all. So in this second part we will apply wind loads on this model and run a structural analysis. First, a few things. We see that the membrane is white on one side and is transparent on the opposite side. This means that the white side is the positive side of the membrane and the other one is the negative side. This is important when we apply loads. A positive pressure will push the positive membrane side. So a positive pressure will push it from upwards downwards. A negative pressure will pull. It will be an uplift. Again, when we do the patterning, the white side will be the top side of the patterns. So this is a very nice information, so we don't make mistakes when we are loading. It's not nice when we are doing a perspective view to see how this model works. And for this purpose, if we go into settings, we can activate double-sided materials. With the double-sided materials active, if we select the membrane and change the material, now the material is double-sided. So for example, let's go into the, I have recall it, right click, tools, render, and let's activate the sun. Choose an hour of the day, enable a ground plane, and to see the sun we need to activate here real-time shading. So now as we move the month, we can see how the sun moves. Okay, and this is very nice for membranes. Generally we want to know, since they're made for shadowing systems, we want to know if they're effective, if really they make the shadow that we want to have at a certain hour. Okay, deactivate the sun, deactivate the ground plane, and close this tool here. Applying loads, the first thing we do, right click on the load tool, load manager, we create a new load, and this will be a self-weight. A self-weight, once we have activated a self-weight load, this is a special load, and we don't have to fill it with anything. The software will calculate in automatic the self-weight of the structure and apply it in the loads. So new load, this one here will be a wind load, and it will be our wind in the X direction. New load, wind load again, and this is our wind in the Y direction. That's it. So for loading purposes, I need only to select the membrane mesh. So we can go down here in the filters and click on no filter and mesh, only mesh filter. So if I open a window, I'm selecting only the mesh elements. Let's look from top. So this is my X direction, the horizontal direction, and my Y direction is the vertical direction. Since the structure is for the X direction is symmetrical, we will make only one load case in this direction. We would need two load cases for the other one, but for making this tutorial short and simple, I will make only one. Now I have made here a table where we can see the loading areas, the CP values. Here we have the CP values. This is Eurocodes for a conical shape. So we can see that zone A, B, C, and D, and then other zones, and then we have the CP values. So what we want to do now is to select these zones. So now I will select the D zone, the add zone, and save these as selections. So let's go ahead with that, and I will use here the select by polyline. So I will start here. My aid zone will be, let's say, here, and I will go down here and C to close. I will go down here like this and C to close. So I need to select also this one. I will use the select single tool like this. So you see I've made a mistake because I'm too far away from the control, and zoom in to deselect like this, select, and then control to deselect. So as we can see, this is my A. We go here into the select menu, and we call this A Z, because this is my wind in the X direction. Sorry, AX, not Z, AX. Then we click on the Save Selection. Once we have done that, we can recall this, and you see that the selection has been saved. So we will select now. We'll choose again the selection tool and select this other area here. Select single to clear, control to deselect these. And again, this is zone D, DX, save selection. Ask to clear the tool. DX is my selection. Now we have zone C. So again, I will use select by poly and go here, here, C to close, select single, again select by poly, start from the center here, go down to this one, and C to close. This is my CX. C. Save selection. Ask and click to clear the selection. My last selection is zone B. So again, select by poly and start selecting here. Go on the other side, and then we want to go down here. That's it. C to close the polyline, and this is my BX. ESC to clear the command and click to clear the selection. So we have made 4 selection sets. As you can see, as I recall these selections, we can see the selected area. So in the same way, we have made the other selections for the epsilon direction. So these are selection sets, and we can go on applying the wind loads on the membrane. In the extension plugins, we have a special plugin here that will calculate, this is for Eurocodes, will calculate the Eurocode wind pressure based on the reference wind speed. In this case we have 33 meters per second. We choose the area in which the model is placed. These are values from the Eurocodes tables. The topograph factor, I will leave it to 1. And then the CP value. For the CP value we have here, we can input directly the CP value, or we can get a channel, the CP channel. This is useful if we import values from a fluid dynamic analysis package. ixCube is connected to Caedium Simscape, Caedium for fluid dynamic analysis. So we can import CP values from that package and use them in automatic. In this case, we don't have them, so we have to input. So we are going to apply wind loads for the X direction. So the load condition will be wind in the X direction. The zone, I will start with zone A, and if I go to my table, we have that A, the CP value is minus 0.15, and this is these two areas here. So for the CP value we input minus 0.15 and generate pressure values. We go on and recall D zone. This is D zone here. If we look in the table, for D we have 2 values, so we should generate 2 load cases, but in this tutorial, to make it short, I will generate only 1, and I will apply a plus 0.4. So my CP value is 0.4. D and generate values. Then the C area, the C zone, the CP value is minus 1. Generate pressure. The last one, the B area, this one here, the B is minus 0.6. So minus 0.6, and generate pressure values. So we have generated all the loads for a load case in the X direction. Let's change the wind load case now, the wind load in the Y direction, and let's start from A. So for area A in the Y direction we have a CP value of minus 0.15. So here minus 0.15. Generate pressure values. Then we recall B. The B is the area in the backside, and B we have minus 0.6, minus 0.6. Generate pressure values. Then we have the area C in the Y direction. and C minus 1. Generate pressure values, generate pressure, and the last one is area D. D plus 0.4. 0.4. That's it. Close. Let's go back to the FEM tools, save the model. So we have applied the wind loads. We are nearly ready to run the structural analysis. Let's go into the analysis panel. We need to create load cases. Well, I have two loads, so at least 4 load cases. 1.35 here, 1.35 here, 1.5, 1.5. Okay, so these are the load cases generally used for Eurocodes. In the settings, now for analysis we should go a bit lower with these values to get more accurate results, at least for the energy and for the forces, and a bit more load increments here, 25, 25, and then we can say run all. The analysis has worked fine. We can save and let's see what happened. So we can go into the plot options, and now in the active results we have not only the form find, but we have also our 4 load cases. So reaction forces for load case number 1. Here we have 15 kilonewton meter. This is a bending moment. It's a bending moment because it has 2 arrows. Then we have a force here of 5.9 kilonewton. So these are the reaction forces on the ground node. Let's give a look at some other useful information. Let's hide the membrane. Take off the reaction forces and plot the axial forces. Scale them a little bit down. So these are the axial forces in our beam, and let's scale down a little bit the numbers, ranges, labels. The element numbers are those of the beams, so let's make them a bit smaller. And you see that this is the bending moment on the beam, 5.9095 is kilonewton meter. Oh, this is the axial force, sorry, these are axial forces. We are plotting axial forces, so these are the axial forces in the elements. So these are in tension. The vertical mass here is negative, is in compression, nearly 8 kilonewtons, and the edge cables have a 10 kilonewton. They are precessed, and these are the axial forces. Let's give a look at the bending moments. Well, the big bending moments is on the main one. Here we have 14 kilonewtons per meter. This is my bending moments, and maybe we have also here some bending moments, but we have to increase the scale, and we see the other bending moments on the other elements. These are bending moments on the second axis and bending moments on the third axis. So you see that we can also activate bending moment M2, M3. Let's scale it a little bit down. And this is a three-dimensional bending moment. And we see that the main moments are on the center of this, the center pole, and of course on the main pole. Okay. Let's see what happened to the membrane activating the deform shape. Let's unhide the membrane and update the view. So this is the deform shape. Well, it's highly scaled, so let's scale it down. The deformation scale. Here we can set the value directly 1. I want a real deformed scale. So this is what happens when my wind comes in. If I press F3 key, we see what's going, how my membrane moves, like that. F3 key again to stop the animation. The last thing, let's give a look at the membrane stresses. So these are the stresses in the membrane due to the wind loads. We see that they're quite low, 5.36. So they're okay. In the same way, we can check the other stresses. These are stresses for load case number 2. We can give a look at the von Mises stresses. Or let's give a look at the deform shape again for this one. And we see how this umbrella deforms when the epsilon load comes in. That's it. If I want to make a slab, a foundation slab, let's select the node here. Going to create a foundation slab. That's it. The foundation slab is not a structural part in the sense that it does not belong to the structural analysis model. But we have a plugin here. If I double click on the footing, filter, select all, double click on the footing, we have all the parameters of this slab. Of course, this is a default size of 1 meter by 1 meter and the height of 0.5, and the amount of steel 0.15% of the concrete, and the position is in the center of the node. We need another material to do a check of this, and if we go into the materials and we get a concrete, we make a new property with the concrete and add it to the model. So we can apply this concrete to our slab. What I would like to know now is how big my slab should be, and for this purpose we have the plugins footing check. The footing checker can calculate both the size of the footing slab and the steel rebars. In this case I want to calculate both, so we need to input here the minimum dimensions of my footings. So 1 meter, 1 meter, the width minimum 1 meter, maximum 2 meters. The height, I would like to say that the height is from 0.5 meters to 1 meter. The footing check parameters, the concrete cover offset, this is the distance between the steel rebars and the concrete. These are how many bars minimum number of bars of 12 millimeter diameter. If we need more reinforcement bars, please use 16 millimeter diameter. And the minimum space between the bars is 6 centimeters. Parameters we can call check footing, and we see here that he has checked and designed the footing. The size is 100 centimeters by 180 centimeters and 50 centimeters height. He's printing the stresses on the 4 corner points. We see here that this is compression on the ground on 2 points, and on 2 points we have reached a tension, so the stress went to 0. If we are happy with this concrete, we can flag it. Flag this one as done, and we can ask for the drawings. So this is the concrete drawings of the slab. Or we can go and give a look at the report, generate the report, and umbrella report, save it. Okay, so we see now, after checking the slab size has changed. It is clear how now it's nice this slab has been designed. The orientation of the long size is in the direction of my umbrella. If I select my slab and go to the properties, we can see now that the compute is nothing. That means that the slab steel rebars and size has been computed. The last thing I would like to do now, very fast, is to check my steel. My steel, remember, is in the mast, and then we have this FEM 2D group. So I would like to check the steel inside those groups. For this purpose, I can recall the steel checker. The steel checker will show me all the groups where we have steel elements, and then the load cases. So I check here to say, okay, I want to check for all the load cases. You double click on a group to see the elements in that group, and in this case we see that here's the mast is a beam element. There's only one element, and made out of 35 pieces. The length of the element is 5 meters 65. The buckling length is 565, and that's it. So to check it, we just recall this check, and you see he says the software is telling me that the beam is not verified. The safety factor here 0.8. 0.8. This number here should be bigger than 1 to be in a safety area. And then I have a detailed report where the software is telling me what's going on. So we can go, we see that the element is not verified. We can go and choose another cross section. This is a 5.4 millimeters thickness, so I have added here another one with 8 millimeter thickness. Once you change the cross section, the line becomes white. That means that we need to check it again. So I check the element again, and we see now that the safety factor, the minimum safety factor, is 1.2. The row is green, and that means that this profile is okay. So that's fine. We can close, and my profile has been changed. Of course, after changing the profiles, we should run a structural analysis again to verify, because the overall stiffness of the model has changed. And that's all for this tutorial. Thank you.